Hi everyone! Starting this video, I will be covering a new topic called crystals. So we'll be putting our SCHO lecture series on hold first because crystals is something that I'm studying right now and something that interests me, and I can't wait to share it with you. So before we begin to cover what crystals are and what are the different structures as well as properties of crystals, I think it's very important to cover a bit of mathematics first. So in this video, I'll be introducing to you what are lattices and what we call a right-hand system and how dimensions and linear dependence work, as well as some notations that we use to define positions, directions, as well as space inside crystal system. And I'm also going to link a bit of mathematics that we learned in high school here, which is the dot and cross product, and that would be really important for us to help us find relationships between directions and planes inside a crystal. So without further ado, let me start with an introduction of what is a lattice. So the official definition of lattice is a regular array of different points. A regular array of points that just repeats periodically throughout space, and the view you have at each point is similar to that from another point. So to demonstrate this, which really sounds like a mouthful, let's consider this this lattice. Okay, so I shouldn't call it a lattice yet because it's just a two-dimensional array of points. It doesn't have to be two-dimensional, and later on we can move on to the three-dimensional case, but just imagine this repeated through space. So it continues infinitely. So to get from this point to this point, you just have to move by a vector A. To get from this point to this point, you just have to move by a vector B. So to get from this point to any point inside this 2D array, you just have to do a combination of A. So for example, you want to go from this point to this point, then you just have to move by 2A and 2B. And to get from this point to this point, you just move by A and then B. So you get what I mean. So in this array of points, to move from one point to another, you just have to do a linear combination of A and B. So this R is just the vector from one of the lattice point to another. And again, because this arrangement of points is periodic and it repeats through space, this holds true for all the points. Now, your 2D array doesn't have to look like this. This is also a possible arrangement. So you might notice that there's a hexagon shape here. And here, the vectors can be A and B. And to move from this point to this point, you just have to do A plus B. And to move from this point to this point, you just have to do A plus B. So you just have to do A plus B plus B. And that will help you get to any point inside the lattice. We can consider other things as well. So, for example, if instead of a hexagon here, we have a pentagon. And the reason why we can't form an infinite array of points using a pentagon is that if you call this A and you call this B, you can't get from this point to this point using purely A and B. And that's why this is not a lattice. Well, these can be lattices if they are repeated periodically throughout space. So with that, I guess we have covered what a lattice is. It is just you have your lattice points, and then you have to put something at each lattice point. And because each lattice point is identical and indistinguishable from any other lattice point, this something has to be the same at every lattice point. So, same something at each lattice point. And this is what we call a motif. I'll come back to this probably in the next video. So we're not going to dwell on this too much, but this is just something we should keep in mind. So a lattice is just lattice points. So those are points that repeat infinitely through space, plus the same something at each lattice point that we call motif. So yeah, lattice has been covered. Now let's define what a right-handed system is. Imagine you have your x-axis and you have your y-axis on the plane of this paper. Where should the z-axis point? Does it point out of the paper or into the paper? Can it point sideways? The answer is we have to use our right hand. So the first thing we should do is to align our fingers. So we can align 4 of our fingers, namely the index finger, middle finger, ring finger, and your pinky. You align all 4 fingers to the x-axis. And then you curl your fingers towards the y-axis. Now, where does your thumb point? That's very important because your thumb points to the direction of your z-axis. In this case, it points up. So the z-axis is actually coming out of the plane of the paper. So can the z-axis be sideways? Yes, it can, but it has to be above the plane of the paper. It has to point up towards the above the plane of the paper. So, does this have to be the x-axis and this be the y-axis? No, it's just a name that we give our axis. And do you have to use a right-handed system? No, but if you do, then people are going to understand you better. And that's why generally in material science and in chemistry, we adopt a right-handed system. So we can also make this the y-axis, we make this the z-axis, then this will be the x-axis. So it just has to go in a cyclic order. So you can have your x, y, z, you can have your y, z, x, you can have your z, x, y. It just has to be cyclic. And then your right-handed system, which is determined by the your finger curling, will work. So you curl your finger from X to Y, that gives you Z. From Y to Z, that gives you X. And from Z to X, that gives you Y. So that's all there is about a right-handed system. And now we're going to cover dimensions and linear independence. So what are dimensions? So imagine we have a line with no thickness. It's just a line. That is one dimension. So what achieves one dimension? You can just have a vector. And with this vector, you can get anywhere on this one dimension. If you're really interested in this, there is a video, I believe it's called The Introduction to Linear Algebra by 3 Blue 1 Brown, that introduces this concept quite well, and you can check it out if you're interested. So coming back, we can have 2 dimensions as well. And what is 2 dimensions? It is a plane. Well, it can look this shape, it doesn't matter. It just and in fact, it can be infinite. Anyway, what is necessary for 2 dimensions? Well, to get anywhere on this plane, you have to have 2 vectors, A and B. It doesn't matter where A and B are pointing as long as they're not pointing in the same direction. So if A and B are both pointing in the same direction, that's very bad because that will give you back your 1D case. So A and B, they cannot be collinear. And that's all you need for a two-dimensional space. So your A can be this, and let's say your B can be this. And with just these 2 vectors, you can get anywhere on this 2D space. Similarly, if you have a 3-dimensional space, you have to have 3 vectors, A, B, and C. So if A, B, and C are coplanar, that means if you have A equals to mu C plus lambda B, which means your A is a linear combination of vectors B and C, which means, for example, you have this, your A is just your B plus your C. That is very bad because all 3 vectors are coplanar, which means one of the vectors is actually not necessary. So that just means that you are back at a 2D case. So to go from a plane to something that has volume, A, B, and C cannot be coplanar. In other words, if you have something that has volume, so for example, you can take your phone to get from any point on your phone to another point on your phone, you have to have 3 vectors that are not on the same plane. So you can have your A and B on the plane of the paper, but you can have your C that points out of the plane. Obviously, this is going to be very hard to draw because your screen is 2D, but you can have your C that's coming out of the plane, and with a linear combination of A, B, and C, you can get anywhere in this world because this world is 3-dimensional. So what is the mathematical representation of this non-coplanar property of vectors, or this property that we want in order to have 3D space? Well, this can be represented with an equation. If alpha A plus beta B plus gamma C equals to the 0 vector, so that means if you start with this point, in order to get back to this point, the only solution is if your alpha, beta, and gamma are all 0. Why is that the case? Because because A is doing its work, B is doing its work. It's allowing you to move anywhere on this 2D plane. But because C has done its work, you are already, so to say, above or below that plane. And to get back to this point, it is impossible without alpha, beta, and gamma all being 0. So this is also what we call linear independence. So if and only if all the coefficients are 0, and A, B, and C are not 0 vectors, meaning they have a length. If only these two conditions are true, then we have linear independence between alpha, beta, and gamma. This, in fact, goes beyond the 3 dimensions. So the number of dimensions equals to the number of linearly independent vectors you have. I'm not going to go through dimensions that are above 3D because we don't really use them. We're not going to use them at this stage. But this is something that's just quite good to know and really important in mathematics. So with this, we have covered dimensions and linear independence. Now let's move on to the interesting part. What are these notations and how do we use them? So let's define a right-handed system. You have your y here, you have your x here, and you have your z here. So y and x kind of form this plane, and z is perpendicular to this plane. Note that just because we have 3 dimensions doesn't mean these 3 axes need to be perpendicular to each other. When it is perpendicular to each other, then we have our normal Cartesian system. So the Cartesian system is actually just a special case for our 3 dimensions. Anyway, we can have our y and our x and our z. Now let's define a vector along each of these axes, a, b, and c. And let's define the length of a, b, and c to be the same as the side of a unit cell. So I didn't really introduce what a unit cell is just now, but just imagine it as a structure or a component that repeats through space. So if we have a unit cell here, then whatever is in that unit cell will repeat above, behind, to the left, to the right, in front of, and below it. And it will go on just infinitely. So for example, if we have something like this, then you will have dots here, 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 here. As well as in front. Well, you get the idea. So it's basically to simplify matters, imagine you have a 3D array of points. You have a 3D array of lattice points. So for example, imagine this, but this will be the first layer, then you have a layer on top of it and another layer on top of it at regular spacing. So imagine you have that, and then you are just going to build a unit cell So for example, you build a unit cell like this, and then you enclose some points inside the unit cell, and then when you construct a unit cell immediately next to it, they will contain the exact same thing, because remember, the lattice points will actually repeat periodically through space. So your unit cell will be enclosing the same thing. However, you have to choose your unit cell well. So for example, let's consider the two-dimensional array of points. If you choose your unit cell as this triangle, this flat triangle, then it actually doesn't work, because because if you just kind of repeat it, you're actually missing out this space. So here you can have a parallelogram as your unit cell, because that will allow you to kind of connect all the dots. Of course, this is not the full picture. I will be covering more about this in the next lecture. Or you can have something like this. So it just repeats infinitely. Yeah, anyway, so that's what a unit cell is. Now, let's define this length to be A, this length to be B, and this length to be C. So, the magnitude of the vectors are basically A, B, and C. Having covered what is a unit cell, let's now talk about how to find how to represent directions within a unit cell. So, for example, what is the direction of the line passing through this point and this point? Well, firstly, we have to take one of this point and we define our origins at that point. So note that we have to use a right-handed system, and for our convenience, we should place the axis parallel to each side of the unit cell. So that is your y-axis, this is your x-axis, and this is your z-axis. Then we just have to use our vectors. So we move by A along the x-axis, because remember, we define A as the length of the unit cell, and the direction of the x-axis, which we have placed along the side of the unit cell. So this will be your vector A, this will be your vector B, and this will be your vector C. So the direction of this line is simply 1A plus 1B plus 1C. So that's the direction of this line. So how do we put that in our crystal notations? So we simply have to not write A, B, and C, and we can put the numbers, the coefficients, in square brackets. So that will be 1, 1, 1. Let's try another example. What if we want to define the direction of this line? So what if we want to define the direction of this line? So in this case, we are moving by half a unit of A, half a unit of B, and 1 unit of C. But in crystal notations, we can't write fractions inside the square brackets. So what we do instead is we have 2r equals to A plus B plus 2C. So we just multiply the entire equation by 2. And because 2r is simply a scalar multiple of r, they are parallel to each other, meaning we are still referring to the same direction, and that will help us get the bracket notation we want, which is 1A, 1B, and 2C. Now, what if our r equals to negative half A plus 1/3 B plus 1C? In that case, we just have to multiply both sides by 6. That will give us 6r equals to negative 3a plus 2b plus 6c. And the notation will simply be 3 bar, that is negative 3, 2, 6. So we can't really say that the position of, let's say, this point is necessarily 1, 1, 1, because in a crystal lattice, all the lattice points are the same, because we define them to repeat periodically through space. So our origin can be at any point. So when we say 1, 1, 1, that just means we are referring to a general direction. We're referring to that one direction. And to say that it is the positional vector of a point inside the lattice, we must first define an origin. Conventionally, this origin is defined at the bottom back of the unit cell, but to be clear, we need to state where our reference point is. So this is kind of like your vector equation of a line. So you need to have your A point and then your lambda direction. So this A point basically fixes the reference point. Similarly, if you want to say that the position vector of a certain point inside the lattice is this, you need to define where your reference point is. Okay, so that's all you need to know about lattice directions for now. Let's move on to planes in a lattice, because remember in high school we learned about equations of lines as well as equations of planes. So both are pretty important, and because we have a 3D system here, it is important for us to be able to index planes. So, for example, if you have a plane, if you have this plane, how do we define its position within a unit cell? Well, the first thing to do again is to define an axis. So if you define your axis here, you will see that the plane intersects the z-axis at 1c. It doesn't intersect the y-axis at all, and it intersects the x-axis at 1a. So the notation for this plane will simply be 1 over 1a (1 over 0b 1 over 1c). And the way we write this is 1 over infinite b, because it doesn't intersect the y-axis. So, and then you just write 0 here and you write 1 here. So again, we don't write in the a, b, and c, because we know what they are. They're just the length of the unit cell, so we don't write them in for simplicity. Now, you might have noticed that 101 is no different from 1 bar, 1 bar. That is because you just have to take another reference point, and that will give you back the same thing. And why this works is simply because your unit cell repeats through space. So these two are the same. Now to demonstrate this, let's consider this surface of a unit cell. it is parallel to the YZ plane, so it doesn't intersect the Y or the Z axis. Therefore, we just have to, its index is 1, 0, 0. However, you notice that since this unit cell repeats through space, this surface we have is no different from this surface of the next unit cell. But if we have that surface, then it intersects our x-axis at 0, which is not good because 1 over 0 gives you infinity. And we can't just put infinity inside these brackets. So we go back by one more unit cell, and then this plane will intersect your x-axis at -1. So that gives you an index of 1 bar 0, 0. So that's why these two planes are exactly the same. Now, let's try another example. What if you have a plane like this? What is its Miller index? Oh yeah, by the way, this is called the Miller index. Well, if you take your axis at this conventional point, you will find that this plane doesn't intersect the axis within the unit cell, even though it should. As in, even though we want it to intersect, we want to find an intersection point. Well, in this case, what we can do is we can shift the position of the origin. So, for example, let's pick another origin. Let's pick this point. So that will still be your y-axis, this will be your x-axis, but this will be your negative z-axis. So the red plane intersects your y-axis at half b. It doesn't intersect the x-axis, so it intersects at infinity a. And it intersects your negative z-axis at negative 1c. So we just have to take the inverse of all these coefficients, and that gives us the Miller index of 0, 2, 1 bar. So that would be the equation of this plane. And some planes that are parallel to it. So, what do I mean by some planes that are parallel to it? Well, let's consider this example. As I have explained just now, the front plane and the back plane are actually identical to each other. So that is the case for the slanted planes as well. And something that's important is for us to find how far apart are the parallel planes, how far apart are the same planes that repeat throughout the lattice. Because remember, the lattice points repeat periodically through space, then the planes within these lattices will repeat periodically as well. So how far away are they? Well, let's consider it in a mathematical sense. So for maths, we can have a plane, we can have a point. Then the closest distance between this point and the plane will simply be, so for example, let this point be the origin so it's easier for us to work with. Then you can take a point on this plane called, let's call it A. You connect O and A. And then, yes, you simply have to take the dot product between OA and the unit normal of the plane. So, in our case, because of the way we have defined the Miller index, your OA times your normal, which is what your Miller index can act as, will just be 1. So, for example, a point on this plane would just be 0, 1/2, and 0. And when you do the dot product of this together with this, you will always, together with the Miller index of the plane, you will always get 1. So that's what it means. So your OA times your normal will just be 1. Your OA dot your normal. So this is the dot product. Then let's name this point B. So the interplanar spacing will basically be OB. So that's our interplanar spacing. Because imagine you have another plane passing through the origin here that is parallel to this plane. So your OB will be your OA times the normal divided by the magnitude of the normal. So this normal divided by the magnitude of the normal will give you your unit normal. So the reason you need unit you need a unit normal is because of this. So your dot product of your A dot B will be your A magnitude of AB cos theta, and the OB you want here, the distance OB you want here, will simply be your OA the magnitude of OA cosine of theta. This is simply by trigonometry. So to get this, you just have to use OA times n, so that would be A times B divided by B. So that's your magnitude of n, and that will give you this this expression, which is just the length of OB. So because we know OA times n equals to 1, so this doesn't have to be a unit normal. This just has to be n. So that's just your Miller index. So this is not a unit normal, this is just your Miller index, and that's your index of a point, of a point from the origin you have defined. So because OA times n is 1, OB would just be 1 over n. And we know n is equals to h over a. So h is your first number in a Miller index. K over B and L over C. So this is K and this is L. And they have to be over A, B, and C because of this operation we have done. Now substitute this into this expression. We get the interplanar spacing will be 1 over h over A squared plus K over B squared plus L over C squared. Now, if we have a cubic system, meaning A equals to B equals to C, that gives us D equals to A over H squared plus K squared plus L squared, because you just have to multiply by A, or B or C, because they're equal. Just have to multiply it in both the denominator and the numerator. So that only works for cubic system. Okay. Another important thing that we can do is we can find the angles between two directions inside the lattice. So from our dot product, we know cosine theta equals to cosine theta being the angle between R1 and R2 will simply be R1 dot R2 over the magnitude of R1 and R2. So R1 and R2 are simply the directions inside the crystal lattice. So we usually denote the directions with UVW. So your cosine theta, so let R1 be U1 V1 W1 and R2 be U2 V2 W2. So we must also consider how long the side lengths of the unit cell are, because the UVW here didn't really include your A, B, and C, but you know that R1 equals to UA plus U1A plus V1B plus W1C. So you can't ignore these the A, B, and C inside your dot product. So what you will have is then cosine theta equals to U1 U2 A squared plus V1 V2 B squared plus W1 W2 C squared. Remember, A, B, and C are just the lengths of the unit cell that would usually be provided to you. That would be U1 squared A squared plus V1 squared B squared plus W1 squared C squared times U2 squared A squared plus V2 squared B squared plus W2 squared C squared. So that will give you the cosine of the angle between two directions within your lattice. Finally, we know that if a line lies in a plane, then the line must be perpendicular to the normal of the plane. So if we have a lattice vector, or a lattice direction vector representing a direction, let's say this vector is UVW, and UVW would be we represent this direction vector, which is R equals to UA plus VB plus WC, and then the Miller index will correspond to something like this. R equals to H big A times big A plus K times big B plus L times big C. You don't really need to bother about what big A, B, and C are, but they're kind of like the opposite of small a, B, and C. So when you have A, small a times big A, that will basically give you, if you have your small a dot your big A, that would just give you 1. So that's all you need to know about this right now. But if you want to learn more about it, then you can watch some videos, maybe by other YouTubers, about reciprocal basis. So yeah, that's all you need to know at this stage. So when we take the dot product of these two, because they're parallel to each other, because they're perpendicular to each other, you should get 0. And that will give you your important equation. So if you have your plane HKL and your direction UVW, if they're perpendicular to each other, then this relationship must be obeyed. So you can see doing this dot product is the same as doing a dot product of these two vectors. Oh yeah, another thing to mention is, let's say big B, when you have big B dot small a, that gives you 0, big B dot small c, that gives you 0 also. So basically the big thing will cancel with everything else. But when dotting it by the small version of itself, or by the reciprocal version of itself, then that will give you 1. That's why when you expand, when you have this dot this, and you just expand out all the terms, you get this times this, this times this, this times this. These two will give you 0, while this will give you u times h. That's why you can just do a direct dot product of these two vectors, and then you just have your u times h, k times v, and so on, directly giving you this result. Yeah, this is just math. You don't need to really focus on it that much, but this relationship is a must know. Now if I have the equation or the Miller index of two planes, we have this plane and this plane, then to find the direction of the intersection, you simply have to take the cross product of these. So the direction of the intersection will be perpendicular to both normals of the plane, and that's why you can just do a simple cross product like this. I realized that I haven't really explained what these brackets mean. So these are called families. So for example, we have introduced Miller index as well as direction vectors, these two. So when you have something like 100, that just means you are referring to all the directions in this family. So these directions are 1, 0, 0, 0, 1, 0, 0, 0, 1, bar 1, 0, 0, 0, bar 1, 0, 0, 0, 1 bar. So all of these directions fall into this family because they are related by you changing the directions, by you like flipping the axis. So for example, when you have your you have your X, Y, and Z, you can kind of change your Z with Y, X with Y, and you just change them. And then because of these changes that you have made, you can just obtain all these permutations of direction vectors just by changing, by interchanging the names of your axes. Of course, this is only a cubic system when all the axes are interchangeable, because A equals to B equals to C. When your A is not equals to B, but A is equals to C, then you can only interchange the X and Z axis. And then you wouldn't have 6 permutations. And the number of things you have in a family is called multiplicity. Similarly, this bracket indicates a family of planes. So for example, if you have 1, 0, 0, that basically gives you the Miller index of 1, 0, 0, 1 bar 0, 0, 0, 1, 0 bar 1, 0, 0, 1, 0, and so on. Well, you get the idea. So if you have something like 1, 2, 3, then this family, if the system is cubic, then will give you a lot of permutations. So the way you list all of them to find the multiplicity is basically you can write 1, 2, 3 here. Then you just kind of permutate these numbers first, and you can get 1, 3, 2, 2, 1, 3, etc. And then you can put bar on top of each of these numbers. So you can have 1, 2, 3, but with a bar on 1. 1, 2, 3 with a bar on 2. Well, 1, 2, 3 with a bar on 3. And then you can do 2 bars. 1, 2, 3. 1, 2, 3. Well, you get the idea. The last one would be 1 bar 1. 1 bar, 2 bar, 3 bar. And then you just have to multiply how many you have on this axis with how many you have on this axis. Well, I don't know how many there are, so let's say there are X here and there are Y here. Then the multiplicity will just be X times Y. Of course, if you have the case where A is not equals to B, then you can't interchange the A and B axis, and some of these combinations will be invalid. So yeah, with that, I have introduced what these notations are, and I have introduced some uses of the dot and cross products. So I guess that's almost all the math you need to know at this stage. And I hope you didn't find this video too boring, because we'll be building on a lot from all these notations, and that will give us a lot of useful results and explain a lot of observations in crystal. And I hope you will follow along with this series, which I'm quite excited to make. But I'm also quite nervous because it's my first time learning all these, and I might make mistakes, and I'm doing these videos really late at night, so I'm having brain fogs. So yeah, if I make any mistakes or I misrepresent any concepts, or I just totally got it wrong, please let me know. I'll be more than happy to correct myself. And thank you so much for watching. I'll see you in the next video.